So let's go through this assignment here. So question 1, what type of a reaction is shown below? Well, we see that we have a leaving group, and that leaving group has been replaced with a OH, and that is a substitution reaction. It's not a elimination because the elimination reactions give us alkenes, so that's off. A proton transfer is off the table because we're not moving any protons around. And then an acid-base reaction right here, we're not doing any acid-base chemistry. And so by process of elimination, you would get to the correct answer, or that you see what's happening here. We're doing a substitution. And so question 2 here, we see that we have a O-tosylate. Okay, so I'm just going to represent it like this. We have an O-tosylate, which is a good leaving group. We look at the conditions right there, and that is sodium iodide, which means it's just a I minus, the iodide right there, and that is a strong nucleophile weak base. We also see that we have acetone, which is a polar aprotic solvent. So that all is screaming SN2. And so our iodide is going to come in here and do a SN2 reaction, which will give us this species right here. The iodide have to come in backside attack, so that would be a wedge. And that's the product after the first reaction. Now the second reaction is we have to treat that with sodium cyanide. And so that's an ionic species, so that's negatively charged. DMF is a polar aprotic solvent as well, and so that's screaming SN2 as well. So that would have to do backside attack to give us the product here. And so that backside attack, so that's dashed like so. Okay, so that's that. That's the answer, and what's that right there? Yeah, so you can do 2 SN2 reactions right in a row. So pay attention to the number when it's numerated like that. Do the first one and then the second reaction. Do it in order that it's suggesting, okay? Question 3, it specified that we had a E1 and an E2 right there. And so substitutions is off the table. And so what we realize with the E2 reaction, that is done in a concerted fashion or in one step. And if we have only one step, then we should only have one transition state. With an E1 mechanism, you are going to have 2 steps. And so that's going to have 2 transition states. So you would have to have something more like this, like that for a E1 mechanism. So based off of that image right there, we would say that can only be an E2. Which of the following will the following alcohol undergo rearrangement during a dehydration reaction? Well, when we look at the first step of the mechanism, what happens under dehydration, we're going to have hydronium. And so that's going to come in and grab that proton because we are under acidic conditions. And so that is going to give us water. That is now a good leaving group. And so when it leaves, we're going to generate a secondary carbocation. And now we are going to do a hydride shift. Sorry, not a hydride shift, an alkyl shift, where this methyl group here can shift over. And when that shifts over, we're going to have now a tertiary carbocation. And where's that carbocation going to be? It's going to be on this carbon right there. Okay, so yes, it can undergo it. Yes, it will undergo rearrangement. to get that more stable tertiary carbocation. So that would be that one right there. Let's see, question 5. What is the major organic product of the dehydration reaction? Well, just like we did above, we're going to have our benzene ring, our OH. The first step would be hydronium. Whenever you have sulfuric acid, there's going to be water present. And so water plus sulfuric acid generates our hydronium. And so our hydronium is going to act as the acid. And then we're going to get this guy right here. That's going to be water now, which turns into a good leaving group. So that means it leaves. And so when that leaves, we generate a carbocation. And now we have to pause and say, hey, that's a secondary carbocation. Can it rearrange to something more stable? And some people would say, hey, there's a hydrogen here. What if we did a hydride shift? Then if we did that hydride shift, what would we get? We would get something that looks like this. And that is also a secondary carbocation. So there's no need to do a shift because there's really no incentive to go from a secondary to a secondary. But here's the kicker though. This one on top right here, okay, that one is more stable than this one at the bottom because it has that carbocation on top is in the benzylic position. It's a benzylic carbon or a benzylic carbocation. And that carbocation this one's more stable than this one below because when you look at that top one, do you notice that if we expand out the double bonds in that benzene ring, what can we do here? We can draw a resonance structure where those pi electrons can come out to help stabilize that carbocation. Okay, so we could have a resonance structure like this. And so that's stabilizing that carbocation. So that right there, backtrack that guy. So this guy right there is the most stable carbocation. And so with that, we can do our elimination with the base. So we are going to have water present. That can act as the base to come in, grab that proton, and put it in between the two carbons there to give us our product that looks like this. Or it could have done it like this. Now, which one would be the most stable? It would be that guy because that's trans. Trans double bond is more stable than a cis double bond. And when we take a look at this intermediate right there, we are going to have free bond rotation around that single bond. And so it's going to rotate in such a way to give us the trans product as the favored product because that's the most stable version between those two isomers. So that right there is our final product and the major product. Question 6. Which choice shows the correct first step of the curved arrow mechanism for the following reaction? Okay, so when we zoom in here, I know it's not the best picture here. What have we done? Let's see. We've done a substitution reaction. So you can see that this CH3, CH2, OH right there, that's called ethanol. What we're adding to the molecule is this piece right there, which you can see right there. So we are doing a substitution reaction. Okay, also when we take a look at this, we have the attacking species, which is weak. So that favors what? SN1 and E1. Now that ethanol, most people know that ethanol is a liquid at room temperature. And so ethanol can also act as the solvent. And so that solvent is a polar protic solvent. So that also favors SN1 and E1. We have a secondary alkyl halide right here. That also, well, that one favors all four mechanisms. But since this answer, or this question, is already showing us that it's a substitution, so we can just, for this problem, just ignore E1 or any elimination. And now we just think about it logically here. It's going to be an SN1 mechanism. Everything's screaming SN1. So if it's SN1, then what's the first step in the mechanism? Well, the leaving group has to leave. And when that leaves, we get this species right here. We get a secondary carbocation. We have to stop. Can we do a rearrangement? And hopefully you say yes, because we have a hydrogen right there that can do a hydride shift, which is going to give us this species right here. We added the hydrogen there. So we went from a secondary to a tertiary. And now our methanol, which I'll just represent like this, ET for ethanol, that can now come in and do our nucleophilic attack, or our attack there. And then we would have it look like this. Oh, and what's attached? What's forming that bond? It's the lone pair that's forming this bond right here. And so we still have the two carbons attached. We still have the hydrogen attached, and we still have that one lone pair that we didn't touch. And so now that oxygen has 3 bonds, so that has to be positively charged. And then the last step would be we would take another ethanol molecule, and that would come in and do our proton transfer step. Let's do it this way, like that, to generate our product. Okay. Now we have to be very careful, because right now the way I'm showing you the mechanism is I'm not showing the stereochemistry. So if we back up and say we look at that carbon, we see that that is sp2 hybridized. So that means it's flat or trigonal planar. So when that when ethanol comes in and attacks, it can attack from the top face or the bottom face. Okay, it has 2 ways that it can approach. And so we could have it approach from, let's say, the top face, which would give us a wedged OH, and we'll just do ethanol like that. So if it attached from the top face, then that would mean the methyl group would have to be down. Or it could have attacked from the bottom face, which would mean that the approach OH ethanol positive, and then the methyl group would have to be wedged. Okay. Am I missing any carbons? I don't think I am. So that's right at this point, that's how you're getting the plus enantiomer, because of this part right here. We have an sp2 hybridized carbocation, so the ethanol acting as a nucleophile can approach from the top or the bottom face, and you have to account for both of those. Okay, So I gave you a whole lot more information for question 6 because all it asked is what's the first step. And that would be the leaving group leaving. Okay, so which would be that one right there. So I gave you more information and some very important information to consider when you're doing these substitution reactions. Okay, so this guy right here is what's the predicted mechanism? Well, it's told you it's SN1, so that means the leaving group leaves. And so we have a benzene ring. We have a benzylic carbocation. So we still have our methyl group there. And that would be a benzylic carbocation, very, very stable. And now our nucleophile, when we take a very close look at that, that is sodium thiol right there. And so that's ionic. So that would have to be like this guy right here, negatively charged. Okay. And so that guy would come in from the top face or the bottom face right there. And so you're going to get a mixture of products. Okay. Okay, so that's question 7. So what would the correct answer be? We're doing... So because it told you it's SN1, you can eliminate that as an option because that's a double bond. That's an alkene. That's an elimination. That's another elimination. So that's off the table. Now, what about these guys? Well, you can't have two wedges on the carbon. And you can't have two dashes on the same carbon. So by process of elimination, that would be the correct answer. But I would hope you wouldn't approach questions like that. You try to solve it just straight up. Look at the reagents, predict the product, and then see if it matches. Question 8. Which choices shows the mechanism for the elimination reaction, assuming that it is a concerted reaction? So that's a hint right there. Concerted means E2. The E1 mechanism is a stepwise reaction. So what would the correct mechanism be? Well, with an E2, what has to happen? The leaving group and the hydrogen being abstracted have to be antiperiplanar. So that's what we're looking for. And in all the answer choices, the hydrogen and the leaving group are antiperiplanar to this bond right here. Now we just have to remember what the mechanism is for E2, and that right there is the correct mechanism. Question 9, which is the aprotic solvent. Aprotic solvents have no hydrogens that can participate in hydrogen bonding. And so which molecules can participate in hydrogen bonding? Hydrogens that are attached to a fluorine atom, an oxygen atom, or a nitrogen atom. Hydrogen attached to nitrogen, so that can undergo hydrogen bonding, so that's polar protic. An oxygen with hydrogen, polar protic. Oxygen with a hydrogen, polar protic. Oxygen atom with no hydrogens there. And then the hydrogens on these carbons, yeah, they're attached to carbon. You don't see carbon in that fun name right there. So that guy right there would be our aprotic solvent, because there's no fluorine, oxygen, or nitrogen atom that has hydrogens on them. And then question 10, it tells us that we have an SN2. And so what's the appropriate SN2 mechanism? So we have answer choice there, 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 and there. We know it has to be a concerted reaction and it has to be backside attack. So the only one that does that would be this reaction right there. That's our concerted one-step substitution reaction. Okay. Then if we keep, and then this matching problem right here. Okay. So I am not going to answer this question in this video because you can take a look at this problem right from your textbook. And it will show you all the answers right there in the end of the chapter. So as always, if you have any questions or concerns, please reach out. I'll be more than happy to help.